Hi everyone, welcome back to the course on quantum theory of many-body systems in condensed matter here at the Institute of Physics at the University of São Paulo. My name is Luis Gregorio Dias. In today's class, we're going to continue to look at those Green's functions. More specifically, we're going to go over the equations of motion that describe or that we can derive for the time-dependent Green's functions. And more specifically, we're going to introduce the so-called Zubarev formalism to write these Green's functions in, or rather the Fourier transform of them. So write the Green's functions in frequency space and have an equation that connects different Green's functions for different operators in the same system. So these are the topics. We're going to start on the actual equation for a given time-dependent Green's functions. I mean, the time derivative of that Green's functions is equal to something. You can look at it as sort of the time evolution for that. And then do a Fourier transform of those and go into the Zubarev notation that I mentioned before for the so-called double time Green's functions. And finish off with an example, the resonant level model, which we can calculate the Green's functions in frequency domain exactly. All right, so let's go right in. Okay, we start with the retarded Green's functions that we saw in the last class. I'll try to remember to put a card here if you haven't seen the class on time-ordered Green's functions. So you get retarded in a given basis for creation and destruction operators that create state in K and M, right? We saw how we can write that. And so is it the retarded Green's functions? These are the operators, either they're bosons or fermions. If they're bosons, this is the commutator. If they're fermions, this is the anti-commutator. And this is the expected value or the thermal average. If the temperature is 0, this is the expected value of the ground state. And the temperature is not 0, then this is the trace with the density operator here is the thermal average or a thermal expected value. So what we want to do is to calculate the so-called equation of motion for the Green's functions. So we're going to show that if I take the derivative with respect to t, the later time, right? The t is larger than t prime. The derivative with respect to t, this is what I get. I get a delta function here plus this other retarded correlation function, which I'm calling d, and we'll have this form. It's going to be like a retarded Green's functions, but instead of the AK operator here, what's going to enter here is the commutator of AK with the Hamiltonian. All right, so let's go to the blackboard and see where and how we get this equation of motion. All right, so let's start by reviewing the definitions. This is retarded Green's functions, which I want to get the equation of motion for. And these are, the operators in the Heisenberg picture, right? Just so to remind ourselves. So let me start by differentiate this guy with respect to t. So this is Km t minus t prime. And I'm going to multiply here by I. That will be made clear later, but the first thing is to get rid of this I here. So I get just d theta dt t minus t prime. And I'll get first here this term here, K M t prime, commutator, anti-commutator, plus I'll keep the minus I here, minus I theta t minus t prime. And then only this term depends on t, so I'll just write this, a k dt commutator, anti-commutator with am t prime, right? That's it. Now, this gives me a delta function, right? This thing. So, okay, I got a delta function there, tau theta minus t prime. And here, well, if they're bosons, right, this is AKT, AKM, T prime. If T equals to T prime, and that's going to be an interesting point later, because now, of course, this is multiplying by delta in t minus t prime. So any integral in t that I make will make t and t prime equal. So this would be a minus here. So t equals t prime, and this will give me a delta km. If they're fermions, this would give me the anti-commutator, and the anti-commutator at the same time will also give me delta km. So as long as I have this delta function here to protect me, I'm fine, should be fine writing this, as long as they go together, right? Delta km, right, this term. Okay, so I got the deltas, and now I have the other one. So I have minus I theta t minus t prime, and this guy here is the equation of motion for this operator in the Heisenberg picture. So this guy is I times the commutator of H and N itself. But here, since I have this extra I here, remember I'm always taking H bar equals to 1 since last class. So I times this is minus this commutator, so is the reverse. So it would be here the commutator inside this either commutator or anti-commutator, but it's going to be another one of AK T H, and then a commutator with that, with AM T prime. Well, it's going to be a commutator for bosons, but an anti-commutator for fermions. Okay. All right, so then I know how to calculate this guy, right? So it's just a commutator with H, and this gives me my equation of motion for the retarded Green's functions, right? Right at the slide that we wrote, delta t minus t prime, delta km minus I, and this is what I'm calling that D, right, which is also a retarded propagator, which is precisely this, minus I theta t minus t prime. There is this commutator here of AK with H, and this is a commutator, and a km at t prime. Then it's either a commutator or anti-commutator depending on whether these are fermions or bosons. Okay. So next step is to take the Fourier transform of that equation. Now, we know how to do that, right? For the retarded correlation functions, we need this omega plus I theta, and then take theta to 0 later, or make the analytic continuation to the real axis. But as this integral in t minus t prime, of the retarded Green's functions in real time. So when I do the transformation here, of course, when I integrate here over t minus t prime, I'll get 1. So I'll have the delta km left. And here, when I integrate and multiply by e to the I omega, etc., I'll get the Fourier transform of this guy. Now, what happens on the left-hand side is, and this is easy to notice, is that when I have a derivative of a function and I write this in the frequency domain, meaning that I take the inverse Fourier transform. So I write this gkm t minus t prime equals an integral in omega. There will be e to the minus omega plus t minus t prime, and here is going to be the gkm in omega. When the derivative of that in Fourier space will only act on this, but remember there will be a minus sign here because I'm taking the inverse transform. So this goes to the derivative of this, which is minus I omega, times this plus I get omega times the Fourier transform. In other words, Fourier transforming this, and that's the other thing that you can actually do, you can integrate that by parts as well, you get an omega plus here times the Green's functions in omega. So that makes my equation of motion in Fourier space, in omega space, much simpler. It would just be on the left-hand side, omega plus times the retarded Green's functions, and on the left-hand side, the Fourier transformer of this other retarded correlation function, and delta km, since I got rid of the delta t minus t prime. So it's much easier to work here in frequency domain because now everything's algebraic instead of having first order differential equations. I have algebraic equations, systems of equations, and so I can start calculating these things. But here's the question: how do I calculate these things? So let's take an example, very, very simple example on how do we actually do a calculation. So here's the free Hamiltonian, right? Quadratic diagonal Hamiltonian. Let's take it to be, it doesn't really matter, it's just fermions or bosons. That doesn't matter because the commutator, either way, if you calculate, and that's the very first step, is to calculate the commutator of the destruction operator with the Hamiltonian. And in this case, as we have done before, is going to be simply the energy associated with this mode, Ek, times the destruction operator. Well, there's a tilde hat missing here, but this is an operator. And this is easy to see, right? So if you either you commute or anti-commute if the operators either commute or anti-commute with each other, this is just going to be the result of this operation. So in this case, this correlation function is just the Green's function, right, times this epsilon, right? So here I have the commutator with the Hamiltonian is just proportional to the destruction operator itself times this epsilon k. So this thing is just epsilon k times the Green's functions, and this is in time. But if I Fourier transform, it will also be just the Fourier transform gr of omega times this epsilon k, right? And so I can just solve algebraically my equations of motion for GR-Km. I have it on the left hand side, I have it on the right hand side. I just solve it. It simply closes. And this is the retarded Green's functions for this systems. for Km is just delta Km omega plus I eta minus epsilon k. So this is, in principle, is a complex function in a complex plane with poles at omega equals epsilon k, if you want, right? In the limit of I theta going to 0. All right, so this is the very first example, which is almost trivial. So let's see how we do more complex ones and how we start from the equation of motion in frequency space from the outset. So in order to do that, I like to use the so-called Zubarev notation. It's a notation introduced in this paper by Zubarev from the 1960s, double-time Green's functions in statistical physics. And I find it very convenient to operationalize, the calculations for these equations of motions. So in Zubarev's notation, he essentially replaces this whole structure of a minus I, a time, a heaviside function to ensure time ordering it, and etc. Plus and this expectation value and this commutator or anti-commutator replaces this whole thing by whatever's in here, right, in this order, A, B, the two operators that are in there, and this double angle brackets here, right? So A, column B, T minus T prime. That's the whole thing here. So you can think of this as T minus T prime is this thing will only depend on T and T prime in this matter, T minus T prime, except if you have some explicit time dependence here or quenches or anything. But so here we're not going to deal into that, but let's keep that in mind. It's as if B is at 0 and A is in T minus T prime, if you want, or T is at T prime, T, and this is just this location. Usually we take it T prime to be 0 and A is at T, right? But it doesn't really matter, as long as you remember that it only depends on the difference. And the Fourier transform is simply the Fourier transform of this whole object, right? And I'll put the index here, whether you are in Fourier space or you're in real-time space, okay? But this is all that we are replacing, right? This whole structure with this notation, double angled brackets. Now, the equation of motion here becomes quite simple. It becomes omega plus the Green's functions, or this doesn't have to be a Green's functions, but it's just this double time retarded correlation function equals either the commutator or anti-commutator, depending on if AB are fermionic or bosonic operators, and the expectation value of that, right? If, for instance, this is AK and this is A dagger M, this will be delta KM. So everything is okay. If not, if there's another term that enters here, it will have to be included there. Say if these A and B are more complex combinations of creation and destruction operators. But then you add another double time Green's functions, or these double angled brackets, of the commutator of the Hamiltonian with A, column B, right? So this will be another Green's functions. If the commutator of H and A is proportional to A, then this is just a closed algebraic equation. If not, then I'll have to calculate more Green's functions in order to construct a system of Green's functions and trying to close it. So let's see how does that work in another example, a little bit more complicated than the free Hamiltonian case. All right, so let's consider this rather simple model, but it's really instructive. which is usually called the resonant level model. So in the resonant level model, we have a Hamiltonian composed of three parts. We have, say, these particles are fermions, right? So what I'm modeling here, I'm modeling a single fermionic level or state. You can think of this as one of the states in an atom, for instance. And this is coupled to a whole bunch of other states, which I'm calling here K, CK, index K, and this is I'm calling index L. And this is essentially has this probability of getting one of the fermions from destroying a fermion here and creating a fermion there, and vice versa, right? So it's like a tunneling effect through a barrier, and TK, it's encoding this tunneling probability, and it has dimensions of energy. So it's similar to the tight binding model that we had, but except that in the tight binding case, we had just another level on this side. Here I have more. I can have, say, a whole Fermi sea of states. And even though they are here described as discrete variables, discrete values for K, it could be continuum, okay? But this is what this model is doing. So I have the Hamiltonian for the level, it's just epsilon naught, which is the energy of the level, times its occupation. So it can be either occupied or non-occupied. So this number can be 0 or 1, right? I have the terms in the band. So I have a diagonal Hamiltonian here. So I have occupations for say the states up to the maximum state, which is going to be my Fermi energy there, right? But so states with energy larger than this will not be occupied, but I'm adding everybody here. And for every state here, there's a probability or a tunnel probability of jumping into the level. So is this quadratic term, which is TK, times the probability of creating a particle at the level L and destroying a particle here, so it conserves particle number. And of course you have the other process of creating a particle here and destroying one there, so the whole thing is Hermitian. All right, so I have now two types of operators. I have these D operators and I have these C's. So they are all fermionic, so they obey fermionic statistics, right? So they are all electrons. So I have to take care of the commutation relations between them here. So what we want to calculate is the spectral function of the level, which is the imaginary part of the diagonal Green's functions. So GL, if you want, I'm just putting L here, but it's the double bracket Green's functions, the Fourier transform of the retarded Green's functions in time for the operators DL and DL dagger, okay, in Fourier space, okay. So I want to calculate this, take the imaginary part divided by pi. Why do I take the imaginary part and divide it by pi? We'll talk about that later at the end of the class. So you want to calculate this quantity, and I'd like to calculate this one first. Okay, so let's start with the first step, which is always to calculate the commutators. So I mentioned that I had two types of operators in this model, so I need to calculate the commutator of each of these instruction operators with the Hamiltonian, okay? And this is what we're gonna get, but let's see how it is done so that you have this idea. So let's go to the blackboard. All right, So these are the different terms in my Hamiltonian. So let's start with the calculation of the, say, dl with h. So this is going to be, okay, let's do the whole thing, right? This is going to be dl with h level plus dl with h coupling plus dl with h band. Well, from the outset we can see that the commutator between this guy and this term is going to be 0. Because why? Because there is no dl operator there. So I'll see this commutator is trivial, is 0. But let's start with this one. So this one might look simple, right? Because this is rather simply looking, but you might want to do it with care, otherwise you might miss a sign, especially for fermions. So this, let's write. See, I'm using the same symbols to denote this L here, the commutator, and the L that appears in the level. So in order to make sure that we're calculating the commutator correctly, let's write level as this, which is equivalent, but let's do it as L sum over L prime, E naught, doesn't matter, dl prime dl prime delta L prime L. Okay, and then we make the sum at the end and make sure that L goes to L prime. All right, but just to get the fermionic signs. Okay, so now let's calculate this. So this is dl times commutator with a level. Yeah, so this dl applied to h level minus h level applied to dl. Okay, so this is going to be a sum over L prime E naught, then I'll have dl, then dl prime dagger dl prime, same thing here, but minus a dl prime dagger dl prime dl, and there will be a delta L prime L here. All right, so this is simply the commutator. Now what we want to do is to try to flip these two guys. So yeah, let's do it this way. So this guy here should be what? dl prime plus dl prime dagger dl should be equal to delta L prime, right? So I can write this guy as dl prime dl prime, actually no, this is delta L prime, sorry, minus this guy. All right, so it should be okay. All right, so let's keep going. So again, I still have the sum over L. I have the epsilon 0 here. I'll have the delta L prime L here. and I have now this in the parentheses. This, I just push this guy to here with a minus sign, so I have another delta L prime minus d L prime dl prime minus dl prime dagger dl prime dl. Okay, so before I do the sum, I'll just notice that these two guys here, they are not in the same order as here, right? And this is crucial. So this is actually minus dl prime dl, this one, right? That's before I do the sum. So if I now switch the two, I get a plus here. Sum over L prime epsilon 0. Oh, there's a dl that I forgot. There's this dl prime here multiplying the delta, the other delta. Okay, delta L prime dl prime plus dl prime dl prime dl minus dl prime dl. So now I can cancel these two. All right, and I can do the sum over L prime. So if I do the sum over L prime, well, the two deltas just become 1, and I get epsilon 0 dl. Okay. Notice that this was important because otherwise, if we didn't do this, we might be looking at these two terms and think they would be equal, but the order is still not the same. Right? So the number here would be off. So this is a common error that can appear. So especially when you're treating Hamiltonians like this, so be careful. With this one, then things are much more clear because you have the sum here. But I made just this artificial sum to make sure that we get the right order. All right? So don't be fooled by that. All right, so I got this. Now let's continue and do the coupling, the commutator with the coupling, which is going to be dl commutator with coupling, and here I'm gonna do it. The only term that is going to matter is this one, because yeah, this one I'll have, well, let's do it, right? Why not? So this is sum in k dl. There's going to be a tk. Actually, yeah, this one is going to be important. dl dagger yeah, let's do let's do this. The tk dl dagger ck plus dl tk star ck dagger dl. Let me maybe I could do that too. Put an L prime here and a delta L prime at the end, so that everybody, yeah, so I'll put another sum in here, so not to make the same mistake as before. I think would be more useful. So okay, minus the other way around, right? So tk dl prime ck dl minus tk star ck dagger dl prime dl, and there's a delta l prime here. All right, so let's keep doing this. Here, this is where I'm gonna need to flip. So I have the sum, yeah. This is the sum over k and l prime. So I have this tk. This is going to be equal to dl prime dagger equals 1, or delta l prime minus dl prime dagger dl, right? So there's going to be a tk, a delta, oops, sorry, a tk, a delta l prime left, this ck, minus the tk, dl dagger dl ck, plus, and now I can do this, tk star. Now dl and dl and ck dagger will just anti-commute, and this will anti-commute with dl prime too. So I get two minus signs here, and I get ck dl prime dl. I take this dl from here, and then here is the two switches, and I get a plus sign. All right. Then minus what? Minus tk dl prime ck dl, which is this one, minus tk star ck dagger dl prime dl. Everything multiplied by this delta l prime. Now, these two, they differ by this exchange here and a minus sign, so I can, just switch the ck with dl here, put a plus sign here, and these two will vanish. These two already have the same form, the same order, so they'll vanish as well. And I'm left with this kl prime tk ck delta ll prime delta ll prime, which is sum over k tk ck. So the commutator of dl with h equals epsilon naught dl plus sum of k tk ck. That's the end result here. Okay, let's go back to the slide. Okay, so we got this. I'm not gonna do the commutator for ck and h. You can do it yourself and check, but it's straightforward. It's very similar to this one, except that notice here we have the tk star, right? Because what's going to give me the contribution is the one where ck dagger appears, so this is tk star. Now with this we go to step 2, which is to write the different Green's functions, the non-diagonal ones. So I have two types. So I have a diagonal in L, GLR, have a diagonal in K, but actually K and K prime, because I have more than one level in K. And I have this off diagonal in K and L too, right? So I have all these three equations, these Green's functions, and they are all related to each other because of these couplings, this coupling TK, right? But they do close, and we're going to see how that works. So let's go to the blackboard. Not sure I'm going to do the whole thing, but at least to give you an idea. Essentially, we're going to use this and this, okay? All right, so let's see how does that work. All right, so we have the definitions here for the Green's functions, and we have the commutators, and I have the equation of motion. So how do we apply this one? So let's give an example here, right? So let's take the first one. Let's write the equations of motion for GLR, okay? So it's going to be omega plus double the operators DL column DL dagger equal expectation value of the, in this case, the anti-commutator of the operator, since we're talking about fermions, right? DL dagger, which is just 1, right? Okay. But let's continue. Now double, here the commutator of D with H. Now I have epsilon 0 DL plus sum in K TK CK double DL dagger, right? Omega is no omega. Now this guy is 1, and so the expected value of a constant is just 1. So I just write here, this is 1. Plus what? Plus epsilon, where is just a constant, comes out. I'll take this term here. Well, these Green's functions is all linear, so A plus B C equals AC plus BC. You can show that just by the definition, just an integral, right? So what we have is this double DL with DL dagger plus a sum in K TK double CK DL dagger. Now notice the interesting twist here. What appeared here is again the diagonal Green's functions in L, precisely the one that we're calculating. And here is the off diagonal GKL, which is that. So it means that the equation of motion for GLR involves other Green's functions. So I get this GL omega plus retarded equals 1 plus epsilon 0 itself, GL omega, plus a sum in K, TK, GKL, right? So it's not closed yet, as in the case. Notice that if TK is 0, then this term is, I get just the free Green's function that I calculated before, right? But here we still have to go another step. So this one appeared, so we have to now go and write the equation of motion for this guy. Okay? This second here. All right. So let's keep on going. Equation of motion for KL. So that would be omega double CK DL dagger equals what? The commutator of anti-commutator of this CK dl plus double the commutator of CK with H, which is written right there, epsilon K, CK plus TK star DL double DL dagger. So this is the commutator here, and I got the DL dagger there. Okay. All right. So yeah, let's call this equation 1. And we're going to derive an equation 2 now. So this guy is 0, right? These guys have nothing to do with each other, so this anti-commutator is 0, so they just anti-commute. Okay. Now I have epsilon K CK dl plus TK star DL. All right, now this is looking good. Why? Because now I have only these two Green's functions to worry about. Because here I have CKDL. Here I still have CKDL, right? So it went back into itself. CKDL plus TK star DL. So this is the other one there. So I have, a system of two equations which I can solve algebraically, right? So I have 1 and 2, and I can try to solve them. So let's see how can we do it. So let's take this equation here, for instance. Notice that we can write, let's isolate GKLR. So GKLR omega minus epsilon K equals TK star GLR omega, meaning that I have GKLR equals TK star over omega plus minus epsilon K times GLR. Okay, which is great, because now I can replace this into here and solve for GL, right? So let's go a little bit down. So substituting in 1, I get this. So let's rewrite 1. I'll have this. Let's see. Oops. Yeah, let's keep 1 there. So 1 is omega plus GL. Yeah, I'll write the R and omega later. Equals 1 plus epsilon 0 GL plus summing K TK times this. There will be a TK star divided by omega minus epsilon K times GL. Now this is a sum over K. There's no K here, so we have this. Now I can close, and so if I put these two to the other side, I get GL of omega equals what? There will be a 1, this one that stays here, divided by, there will be an omega plus minus a epsilon 0 minus this sum here. Absolute value of t squared divided by omega minus epsilon k. All right. So this solves my, so we close this. So I have 1 over omega plus minus epsilon 0, and there's omega here and here. Notice there's an omega plus here too. Well, yeah, let's write this, okay? So notice if t, again, if t equals 0, I get precisely what I had before for the free case, omega minus epsilon 0, so everything is decoupled. But the fact that t is not 0, that these two systems are coupled, adds something to my Green's functions. Add this part here, which, notice, there will be an imaginary part and a real part here, because this is omega plus I theta. So we're going to go back to that. But again, this is just algebraic equations, and they did close. So let's go back to the slide. Let's just remember the result here, and let's go back to the slide. Okay, so we solved the equation for the equations of motions for GLR. Notice that we didn't even need to calculate this one, because already at this level the equations did close, so which is good news. Sometimes we're not so fortunate. But then we have the Green's functions in this structure is 1 over omega plus minus the energy of the level, right? Plus something here. And this something, actually there should be a minus sign. Yeah, well, no, yeah, that is minus. Yeah, it's minus t squared, absolute value of t k squared, omega plus minus omega. And this part that appears here is usually called the self-energy for the Green's functions. Notice that it would be related to the coupling, and as we shall see, this kind of broadens the energy of the level when you calculate the spectral function. So yeah, let's now go in and calculate the spectral function, meaning the imaginary time of this guy, the imaginary part of this guy over pi. So let's see how this goes. So the first task is to look at the self-energy and try to separate its real and imaginary parts, okay? So let's assume that, you know, I can do that, right? In principle, it's just sum over k, that there's that tk squared and omega plus minus this is the expression, right? Precisely here. So the self-energy will have this something like that. Well, sum over k, there will be this tk's omega plus I eta, so there's the imaginary part right there, minus epsilon k. So yes, there will be an imaginary part. It might be small, but still we have to calculate, and there will be an exercise in assignments showing that this can be done by a principal part integration, but in principle this will be a complex number. So let's write this as a real part, which might depend on omega, and plus an imaginary part. I'll put a minus here just so that we have, right? And so that's what we have, okay. But let's say we calculate this, right? We somehow have how these tk's depend on k and so on, and we can perform the sum, and we get somehow we get these numbers or these functions, okay. So my Green's functions will have this form. We'll have something like that. So there will be a real part here, which is omega minus epsilon minus the real part of the self-energy, right? And there will be imaginary parts. There's going to be an I, there will be this eta, and there's going to be, let's see, omega plus I, there's a minus, this minus cancels with this one, so there's this delta here, okay? All right. Now, I can multiply up here and down here too by the complex conjugate, right? Minus eta plus delta, okay? And this will give me a real part, but the most importantly, will give me a real part. But the imaginary part is the one that we're interested, which is going to be minus I delta plus eta, and here we can disregard that. But here is going to be something like this: omega minus epsilon tilde plus delta, yeah, plus eta squared or something. So in the limit of eta going to 0, so this is the Green's functions. So the minus the imaginary part over pi of my Green's function is going to be something like that. Delta over pi omega minus epsilon tilde square plus delta square for eta going to 0. Notice that eta going to 0 doesn't necessarily mean that the imaginary part here is going to 0. We can discuss that this comes from an integral part, and there might be many poles here and so on, but here at least this delta might be small, but might not go to 0 as eta goes to 0, right? So let's assume for now that's a constant, and usually that's a good working assumption, especially if you have many levels here, but I'm not going to go into that. But okay, so this has a Lorentzian shape. Lorentzian. And let's see what we can do with that. So here's the spectral function, and we are assuming this. And this is the form that I calculated. And there's another piece of information that we didn't mention when we talked about the spectral function, is the so-called fluctuation-dissipation theorem. And the theorem states, it relates the imaginary part of the retarded Green's functions with minus I times the lesser Green's functions. And you can see that, as we saw in the class when we wrote both of them, and in terms of the many-particle states, so which is the Lyman representation, that both of them have these Dirac delta functions appearing. So yes, one should be proportional to the other, and the proportionality factor actually comes down to the Fermi distribution function for fermions. Okay, this I'm talking for fermions. So as it turns out, this is something you can derive. It is an exact expression, and it turns out that the occupation of the level has to do with these lesser functions calculated at t prime equals 0, right? Why? Because the level occupation is just the expected value of the number operator at the level at a given temperature, And this is just an expectation value calculated at some fixed time, say t equals 0. And when you do that, you can Fourier transform this, and you ended up with this level occupation written in terms of the spectral function here. And at t equals 0, so the average occupation of the level, which varies from 0 to 1, right? It will be a smooth function of, say, this level here. And we're going to see how does that work in a mathematical script. But at t equals 0, this will be an integral up to, from minus infinity up to the Fermi energy, which we assume, let's say that the Fermi energy is at 0. So remember, in our model where the Fermi energy is just, is just the maximum occupied level of this band here, right? And let's say, okay, this is my 0 of energy. And now every energy in my problem will be measured from the Fermi energy on. So, it's just a reference for the energy where we can calculate these things. So let's look at a mathematical script. How does these things change when I change the level relative to the Fermi energy? So what we're doing is that I can imagine that I can move this level, and in many experimental systems you actually can, relative to the Fermi energy of these electrons. Say that these are metallic electrons. So if this energy is below the Fermi energy, you would think that would be favorable for these guys to jump in and occupy this level. So the probability of having this level occupied is larger than if this energy is much larger than the Fermi energy, so it would be much harder. I mean, the probability for occupying that level would be much smaller, especially at low temperatures. So let's see how does this work if we plot these functions with Mathematica. Okay, that's exactly what I'm doing here. I have this notebook. So I define my self-energy, the imaginary part, which is delta. Let's assume it's a constant. And this real part, lambda. The Green's functions in the dot, 1 over omega minus ED, which is the dot level, the resonant level energy, minus the self-energy. The spectral function of the level, which is minus 1 over pi imaginary of this. And now the occupation of the level, which is the integration of the spectral function from, say, minus infinity, which I'm calling 10 here, to 0, which is the Fermi energy. So essentially what I'm doing is implementing all this, okay? All right, so let's see what he got. Remember, the Fermi energy is at 0. So if the level is way below 0, I would expect that the occupation would be large. And that's precisely what he got. This is the occupation as a function of the energy of the level, of the resonant level. So if the energy is very small, the occupation approaches 1. If the level is ED is way above the Fermi energy, which is right here, then the occupation is small. Okay. So why is that? What happens to the spectral function when I move this level position? So if epsilon is at 0, right? What do I get? I have a Lorentzian shape centered at 0. That's precisely what this is telling me here, right? I have a Lorentzian shape with the width is proportional to delta, and I'm using delta equals 0.1 here. So I have it centered at 0. So half of it is below the Fermi energy and half is above. Now if I bring it over to this side, notice that occupation of the level is the integral of this curve all the way up to 0. So most of the weight is below 0, so I expect a large occupation, right? Now, if I move the level above the Fermi energy, then I move the bulk of the weight above the Fermi energy and the occupation goes down. Right in the middle, I have, right here at 0, I should have, and if this is everything is normalized, right, I would have occupation equals 1/2, which is precisely what I get right there. Okay, so this is a physical consequence of our level. Now why even the level fills up or not? I mean, it is all related to the coupling, right, between the two systems, and that's the T square. So this width, this delta here, has to do with how strong those couplings are. So the larger the couplings, the broader will be this level. The smaller that coupling, the narrower will be this level. In the limit of t going to 0, this should become a delta function, and that you can actually calculate, right? In the limit of delta going to 0, this becomes a delta function centered at epsilon naught. Tilde, well, because it's corrected by this real part here, but it's essentially epsilon naught. Okay? So yeah, this gives a this hands-on introduction to equations of motion and why they are important, precisely because we can calculate things like spectral functions and level occupations and things like that from the fluctuation-dissipation theorem. All right, so next class we're going to look at a more realistic model, which is the Anderson model, which will involve interactions in this level, and we'll see what comes about when we add interactions here, interactions and spin. All right, so see you next class and see you next week.